Hello everyone, this is the last part of our calculus short course series. In the first part, we have revisited the limit topic. We have seen the definition of what a limit is, and we have seen how do we evaluate limits of several functions and different function types. What are the techniques to calculate a limit? And we had a few examples. In the second part, we had two separate videos for taking derivatives, definition of derivatives, derivative techniques, and examples. In the second video of the second part, we have revisited the integrals. We have seen the definition, we have seen the techniques, we have seen some well-known functions and their integrals. Also, we have studied the relationship between derivatives and the integrals. In this last part, we will see how these elements of these topics of calculus are used in electrical engineering. So we will be seeing some applications of calculus. In fact, electrical engineering is all about calculus, so it is everywhere. In circuits, in signals, in digital design, analog design, automation and control, calculus is everywhere. But since it's not possible to cover every single use case, we will be evaluating a little bit more than a few examples. So this presentation will be an example string. We will have a few examples, but these examples will demonstrate a use case. We will see examples related to the Ohm's law, which means that we will analyze voltage, current, and their relationship within a given circuit. Then we will see differentiator and integral taking circuits, the circuits which produce the derivative of the input signal as its output. And lastly, we will revisit the displacement and speed analogy, and we will try to port it to topics of electrical engineering, as well as a few other examples. The first one. According to the Ohm's law formula for a capacitor's current, which is the current passes through a capacitor, is proportional to the time derivative of that capacitor's voltage. So we can represent it in mathematical terms like I equals to C times dV dt, where dV dt is the derivative of voltage with respect to time. Another way of saying this is to state that the capacitors differentiate voltage with respect to time. So what capacitors do is taking the derivative of voltage and express it in the output current. Suppose we had an oscilloscope capable of directly measuring the current, or at least a current to voltage converter that we could attach to one of the probe inputs to allow direct measurement of current on one channel. With such an instrument setup, we could directly plot the capacitor voltage and the capacitor current together on the same display. So if you have ever visited an electrics laboratory, an introductory laboratory or a more advanced one, you will probably see, or you have already seen, an advanced digital oscilloscope, or even an analog one would work well, but could be a little bit tricky to set it up. You can easily plot these voltage and current as signals. In the example, we have three different voltage waveforms shown in the charts in this page. And for each of these voltage waveforms, which are obtained from, let's say, channel B of the oscilloscope, the question asks us to plot the corresponding capacitor's current waveform observed from, let's say, channel A, as it would appear on the oscilloscope screen. So, and there is a little note here: the amplitude of the current plots is arbitrary. It's not important because they are units of voltage and current are not the same. Voltage has volts and current has amperes, and these can be scaled on the oscilloscope screen. So a 1 volt sized wave could be very big on the screen or could be very small. It depends on the size that is set on the oscilloscope. But what is important is the shape of each current waveform. So if you remember what we have done in the previous part of this calculus series, you can stop the video here and try to draw the expected current waveforms on a paper, or just skip this part to see the solution. But I strongly recommend you to try to draw current waveforms, or at least think about it. Here we have the solutions. The blue signals are the voltage waveforms obtained on channel B, and the red ones here are currents. So as you see, we have the exact derivatives of the voltage waveform drawn as the current waveform. Could you please keep in mind that the derivative is all about the change. So if there is a change in a quantity, then that means that there is a non-zero derivative. And an increasing line segment with an angle with the x-axis would yield a linear, a straight line segment as its derivative. So this is why we get here rectangular signals as output of chainsaw style voltage signals. So these chainsaw style voltage signals would yield rectangular signals as output current. The second example here is, as you can notice, is either a sinus or a cosinus signal, or a very similar variation of these trigonometric functions. So it could be a times cosinus x or 5 times sinus x, etc. Doesn't really matter. So it's a trigonometric function. And if we take the derivative of this function, actually you can even find out which function is it, because we have a 0 here in the x and y axes, and here this blue function gives 0 as the result if x is 0. So in this case, the blue one could be sinus, because sinus 0 is 0. And if this is sinus, then the output must be its derivative, which is cosinus. This is why we have two very similar signal waveforms here in this example, because cosinus, the shape of a cosinus signal is no different than a sinus signal, but it's a phase shifted version of its counterpart. In the third one, we have a rectangular voltage as input for the capacitor, and the output current becomes a very thin drag function, like a needle, because the only change in the graph with respect to the time domain is the shorter edge of these blue rectangles. So this is why we have needle style output current here and no current at all in other points. This is also the derivative of this rectangular function. Let's move. Potentiometers are very useful devices in the field of robotics because they allow us to represent the position of a machine part in terms of a voltage. In this particular case, a potentiometer mechanically linked to the joint of a robotic arm represents that arm's angular position by outputting a corresponding voltage signal. So if you ever have dealt with automation, control, embedded design, robotic design, etc., you may have seen or worked with potentiometers, but otherwise this can still be an interesting example for you. Each different position of a robotic arm or another mechanical part would result in a change of the output voltage. Then, by using this variable voltage, we can estimate the current position of this robotic element. As robotic arm rotates up and down, the potentiometer wire moves along the resistive strip inside, producing a voltage directly proportional to the arm's position. So this is how it works. A voltmeter connected between the potentiometer wiper and ground will then indicate arm's position. A computer with an analog input port connected to the same points will be able to measure, record, and if it also has some other connections to driver circuits, it can control the arm's position. In this case, we will need a driver circuit because the output from a computer would be very weak for driving the machine. If we connect the potentiometer's output to a differentiator circuit, we will obtain another signal representing something else about robotic arm's action. What physical variable does the differential output signal represent? So it's an interesting question. By the way, a differentiator circuit, as I briefly mentioned previously, is an electronic circuit that takes voltage, some kind of voltage with as a function of some variable, and make some natural conversions or deductions, and gives another output, gives another voltage function as its output. But here, this output voltage is exactly the derivative of the input voltage. And keep in mind that these are all functions. So this input function is a function of some variable like time. And the output function is also, the output voltage is also a function of time or another variable. But in these cases, usually we use time, because the robotic arm works on the time domain. Its position changes when time changes. So we will keep track of that position using the voltage per time. Let's see the solution. The differentiator circuit's output signal represents the angular velocity of the robotic arm according to the following equation. You will easily remember this equation if you have ever watched our previous videos. Velocity V equals to dx dt, where x is the position or displacement in other words, and t is time. So derivative of displacement with respect to time is velocity. We have studied that previously. So a follow-up question is coming. What type of signal will we obtain if we differentiate the position signal twice? So it's the second derivative. So that connect the output of the first differentiator circuit to the input of a second differentiator circuit. So we will, what this means here is cascading the differentiator circuits. This question asks us to relate the concept of time differentiation to the physical motion, as well as gives us a very practical example of how a passive differentiator circuit could be used. In reality, one must be very careful to use differentiator circuits for real-world signals and applications because differentiators tend to amplify high-frequency noise. In electronics, especially in telecommunication circuits, telecommunication devices, noise is one of the biggest enemies, and high frequency noise usually causes very important errors and should be avoided at even high costs. So this is why we have a warning here. Since real-world signals are often noisy, this leads to a lot of noise in the differentiated signals. But if we have to use a differentiator, this is not the end of the world. We have many filter circuits, filter designs that can work pretty well with avoiding these noises or eliminating these noises if they are already added to the input signal. These band pass or band stop filters are used frequently to get rid of these noises within the original signal. We know that the output of an integrator circuit is proportional to the time integral of the input voltage. So this is why this kind of circuits are called integrator circuits. And here you see an example of an integrator circuit made by using an operational amplifier, or shortly op-amp, a resistor, and a capacitor. So the output voltage Vout could be proportional. Should be proportional to the voltage input with respect to its time changes. Here you see an integral sign, but it is probably because of an copying error. It's broken down, but it is only a single integral, and it's a definite integral from 0 to t. T is time, our time limit. And dt is the varying time sign. So, but how do we turn this proportionality into an exact equality? So, proportionality is good, but in order to use in our equations or our system design, we need exact equality, so that it accounts for the values of R and C. Although the answer to this question is easy enough to simply look up in an electronics reference book, yes, you can find a lot of relations like that online or in books. It would be great to actually derive the exact equation from our knowledge of electronic component behaviors. And the question also gives us a hint. I, capital I, is equal to V over R times I, which is equal to C times dV dt, where dV dt is the derivative of voltage with respect to time. The solution is V out equals to minus 1 over RC times integral. This is also a single integral. Integral from 0 to t voltage input times dt. So this integral when multiplied with 1 over RC, minus 1 over RC, will give the result, which is the output voltage. This result could be reached using these two equations here given as hint, and what we should do here is making substitutions. If you play with these equations, you will easily get which variables should be substituted and which operations must be done afterwards. And if you play with this, you will eventually get this equation easily. And a follow-up question exists here, says why is there a negative sign in the equation? So we should, in order to answer this question, we should ask another question. How come a voltage could be negative? What is the meaning of negative voltage? So positive voltage and negative voltage have the same amplitudes if you take the absolute values. So the magnitude, or in other words amplitude, should be the same. So what is that minus sign? You don't have to be an expert of electronics to answer this. It's also an easy one. This is the phase of the voltage. If you try to plot any trivial function as an imaginary voltage, and if you take the negative of this voltage and also plot it, you will see that there is a phase shift of 180 degrees between these positive and negative versions of the same function. So this is why we have a minus. We have a phase shift in this circuit. There is a lag between input and output voltages. Another example is coming. A Rogowski coil is essentially an air core current transformer that may be used to measure DC currents as well as AC currents. Like all current transformers, it measures the current going through whatever conductors it encircles. Cool, right? Normally, transformers are considered AC-only devices because electromagnetic induction requires a changing magnetic field, and it is represented as d phi dt. So it's derivative of phi with respect to time to induce voltage in a conductor. The same is true for a rogowski coil. It produces a voltage only when there is a change in the measured current. So if the current is constant, then it will not produce a voltage. But if the measured current changes, then it will produce a voltage as its particular output. However, we may measure any current, DC or AC, using a rogowski coil if its output signal feeds into an integrator circuit as shown below. You don't have to memorize it with its details. I put it here because it is very interesting. So it's nice to see, but you don't have to memorize this. Just know how it looks like. We have the coil here, we have a power conductor, and it is attached to an integrator circuit which is identical to the one previous. It's the one in the previous example. And here Vout is also proportional to the input current, which is taken from the power conductor that passes through that rogowski coil. Connected as such, the output of the integrator circuit will be a direct representation of the amount of current going through the wire. And the question asks us, explain why an integrator circuit is necessary to condition the rogowski coil's output so that output voltage truly represents conductor current. The answer is, the coil produces a voltage that is proportional to the conductor current's rate of change over time. So V coil is formulated as M times di dt, where di dt is the currents derivative with respect to time. So it's time varying current. The integrator circuit produces an output voltage changing at a rate proportional to the input voltage's magnitude, and shown as dV out dt is proportional to V in. So derivative of V out with respect to time is proportional to V input. And by using algebraic substitution, we will get dV out dt equals to m times di dt. dV out dt is time derivative of output voltage, di dt is time derivative of the input current, and m is the mutual inductance of the coil. So it's a constant value. You don't have to worry about that. Here we also have a review question. Rogowski coils are rated in terms of their mutual inductance M. So it's expected that you defined what the mutual inductance is and why this is an appropriate parameter to specify for a rogowski coil. I will not give the exact answers for some of these questions, including this one. So you can just stop the video here and Google these terms like mutual inductance or whatever you see here. You can type Google rogowski coils as well. So if you spend some effort, then it will be easier for you to learn and discover the reasoning behind these mechanisms, and then it will be harder for you to forget. Another question is coming with no answer. The operation of a rogowski coil and the integrator circuit that is attached to this coil is probably the easiest to comprehend if one imagines the measured current starting at 0 ohms and linearly increasing over time. So it says qualitatively explain what the coil's output would be in this scenario and then what the integrator's output would be. Here we have even more questions. It's a challenge question. The integrator circuit shown here is an active integrator rather than a passive integrator. So that is, it contains an amplifier, an active device. We could use a passive integrator circuit instead to condition the output signal of the rogowski coil, but only if the measured current is purely AC. A passive integrator circuit would be insufficient for the task if we tried to measure a DC current, and only an active integrator would be adequate to measure DC. And says explain why. Here I suggest you to take a look at what kind of current can pass through capacitors and what kind of current can pass through inductors. And I also recommend you to investigate the relation between the frequency of input signal and the output and the situation of the output signal in both capacitors and inductors. Do they allow low frequency signals to pass or high frequency signals to pass? So if you learn this, if you understand this, then you may have an answer for this question. Unlike the iron core current transformers widely used for AC power system current measurement, rogowski coils are inherently linear, and being air core devices, they lack the potential for saturation, hysteresis, and other nonlinearities which may corrupt the measured current signal, so that they are great. This makes rogowski coils well suited for high frequency and even for radio frequency current measurements, as well as measurements of current where there is a strong DC bias current in the conductor, which happens a lot, believe me. By the way, this DC bias currently may be nulled simply by resetting the integrator after the initial DC power up. So let's do not get lost in these details, but as you see, there is a lot of use of calculus in these transformers. We have another question here regarding rogowski coils. We will not solve it here in this video, but I will give you the answer. And if you want, you can solve this question using the relations given in the previous pages and calculate the result. And the question is, a rokowski coil has a mutual inductance rating of 5 millihenries. Calculate the size of the resistor necessary in the integrator circuit to give the integrator output a 1-to-1 scaling with the measured current, given a capacitor size of 4.7 nanofarads. So here we have the transformer and the integrator circuit just as in the previous example. That is, size the resistor such that a current through the conductor changing at a rate of 1 ampere per second will generate an integrator output voltage changing at a rate of 1 volt per second. Here you are free to stop the video or just rewind back to see the relations between input current and output voltage, and the answer here R equals to 1.064 kilo ohms. So here is the next example. The chain rule of calculus states that dx dy times dy dz is equal to dx dz. It can also be proven in an algebraic way, of course. And similarly, the following mathematical principle is also true. Dx dy equals to dx dz over dy dz. So it is very easy to build an op-amp circuit that differentiates a voltage signal with respect to time. Yes, it is. Such that an input of x produces an output of dx dt. But there is no simple circuit that will output the differential of one input signal with respect to a second input signal. So we can produce the derivative with respect to time, but we produce another derivative with respect to another input signal is a tough job. However, this does not mean that the task is impossible. Draw a block diagram for a circuit that calculates dy dx given the input voltages x and y. So this is the question. And we have a hint. This circuit will make use of differentiators, and we will use the relations given above. And there's a challenge question, says draw a full op-amp circuit to perform this function. It's not necessary, but if you are confident, you can do that very well. Here you see the visual representation of this system. We have two simple differentiator circuits with one input and one output. So since it is a hard job, we do not use or cannot use a differentiator system with two inputs and one output. So we will use the very simple differentiator circuit we have used in previous examples. Actually, we have used integrator circuits, right? Yeah, but this is the differentiator version of it. So it's a simple circuit used with op-amps. We have placed two of these simple differentiator circuits, and we placed another divider circuit which takes the outputs of these two differentiator circuits as its input and produces one output, which is the division of these two inputs. So what we are doing here by using circuit elements is exactly this equation. So we are doing the we want to obtain the x dy, but since the x dy cannot be possible, we use dx dz over dy dz. And the first differentiator circuit takes y and produces dy dt, and the second one takes x as its input and produces dx dt. So the divider makes the division, and we will get dy dx eventually. Differentiator circuits are very useful devices for making live calculations of time derivatives for variables represented in the voltage form. For example, the physical measurement of velocity when differentiated with respect to time is acceleration. Thus, a differentiator circuit connected to a tacho generator measuring the speed of something provides a voltage output representing acceleration. Being able to differentiate one signal in terms of another signal, so means that one function in terms of another function, although equally useful in other topics of physics, is not so easy to accomplish with op-amps. A question such as this one highlights a practical use of calculus, especially the chain rule, where the differentiator circuit's natural function is exploited to achieve a more advanced function. So in this case, we cannot use op-amps very easily, and this kind of a setup is much more useful and easier. The next one. Ohm's law tells us that the amount of voltage dropped by a fixed resistance may be calculated as such: E equals to I times R. Actually, V is used much more commonly for these equations, but here they have used E, so whatever, it doesn't matter. It's just V. You can think of it like V for voltage, equals to resistance times current. However, the relationship between the voltage and current for a fixed inductance is quite different. The Ohm's law formula for an inductor is as such: E, small e, equals to L times di dt. So it's time derivative of current that passes through that inductor times inductance of the inductor. What significance is there in the use of lowercase variables for current I and voltage E? I suggest you to assume that it is V, but again, it doesn't matter. And also, what does the expression di dt mean? Note, in case you think that these are variables and should cancel out in this fraction, think again. This is no ordinary quotient. Yeah, it's not the case, but I assume that you already know that very well. The D letters represent a calculus concept known as a differential, and the quotient of two D terms is called a derivative. So di could only be cancelled out when it is divided by di again. And use of capital letters and lowercase letters for the variables usually mean that the capital letters stand for time constant variables, and lowercase letters are for time varying variables. This is a common notation, but it's not used all the times, so just keep in mind. You may not see it everywhere, but if you see both versions of a variable like capital V and small v, then you may think about that like one of them is time dependent and one of them is time constant. It does not, meaning that it does not change over time. Another point of view, another approach would be lowercase variables represent instantaneous values as opposed to average values. So this statement also holds. This is also true. And the expression di dt represents the instantaneous rate of change of current over the time. And here a follow-up question arises. Can you manipulate this equation to solve for the other two variables, which are di dt and L? and I'm sure you can do that. We have already reached 40 minutes here, and we have quite a few more examples left. So I decided that we should stop here for a good break, and we will continue the rest of the examples, questions, and their solutions in a second video. So we can align our online short courses with the real courses time span. Thank you very much for listening. We will continue on that in the next video.